Look up at the night sky. What do you see? For most of human history, we saw pinpricks of light stars, planets, the moon, all part of a familiar cosmic tapestry. But what if I told you that hidden within that darkness are objects so strange, so fundamentally mysterious, that they challenge everything we think we know about the universe itself? We're talking about dark stars, not the kind you find in poetry or songs, but colossal, invisible giants that may hold the key to understanding the very fabric of reality. These aren't just unseen objects, they're gravitational anomalies, cosmic ghosts whose presence we can only infer from the way they warp space and time around them. For centuries, astronomers have mapped the heavens, cataloging stars, galaxies, and nebulae. Yet some of the most fascinating discoveries are the ones we can't even see. Imagine a star so massive, so dense, that it doesn't emit light, it devours it. A dark star isn't merely a dead star or an empty void. It's a gravitational powerhouse, bending light and trapping matter in ways that defy conventional physics. The concept alone stretches the imagination, suggesting that our universe is far stranger, far more wondrous than we ever dared to dream. In this video, we're setting out on a journey to explore 25 of the most compelling candidates for these undiscovered dark stars, each one a potential game changer in the world of cosmology. From distant galactic centers to the quiet corners of our own Milky Way, these hidden giants could help solve some of science's biggest puzzles: the nature of dark matter, the fate of collapsing stars, even the possibility of entirely new forms of celestial bodies. Strap in, because by the time we're done, you'll never look at the night sky the same way again. Our journey into the unknown begins not in the far reaches of space, but at the very dawn of time itself. Picture the universe in its infancy, a mere 200 million years after the Big Bang. It is a vast, dark, and simple place, filled with a warm haze of hydrogen and helium gas. Yet within this primordial fog, the first seeds of structure are beginning to form, pulled together by the gravitational influence of a mysterious, invisible component, dark matter. It is within these dense clouds of dark matter and pristine gas that the first true monsters of the cosmos were likely born, the primordial dark stars. These weren't stars in the way we understand them today. A modern star like our Sun is a nuclear furnace, powered by the fusion of hydrogen into helium at its incredibly hot core. A primordial dark star operated on an entirely different, almost alien principle. Its immense power came not from nuclear fusion, but from the annihilation of dark matter particles at its core. Theorists suggest that in the early universe, dark matter was far denser and more interactive. As these particles collided and annihilated each other, they would have released a tremendous amount of energy in the form of heat and light. This exotic power source created a celestial object of almost unimaginable scale. While a typical modern star might be 1,000,000 miles across, a single primordial dark star could have easily stretched to 10 million, 100 million, or even several billion miles in diameter. To put that into perspective, if one of these behemoths were placed at the center of our solar system, its surface could easily extend beyond the orbit of Jupiter, engulfing the inner planets. Their sheer physical size is only half the story. The energy output from dark matter annihilation would have been so extraordinarily intense that a single primordial dark star could have outshone an entire present-day galaxy, pouring more light into the young cosmos than millions of sun-like stars combined. Which leads us to a profound and puzzling question. If these objects were so colossal and so brilliantly luminous, why have we never seen one? The answer lies in both their distance and their fate. These giants lived fast and died young by cosmic standards. Their dark matter fuel, once depleted, would have caused them to collapse under their own incredible weight, likely triggering the formation of the universe's first supermassive black holes. The very same black holes we now find at the hearts of nearly every large galaxy. Any light they emitted has been stretched by the expanding universe into the far infrared part of the spectrum, making them incredibly difficult to distinguish from the background glow of the cosmos with our current telescopes. They are cosmic ghosts, their brilliant flash of existence lost to the depths of time, leaving behind only their gravitational echoes and the tantalizing possibility that we might one day catch a glimpse of their ancient light. To understand how such a bizarre object could form, we have to venture into the realm of particle physics and rethink the very definition of a star. A normal star is born when a massive cloud of gas, primarily hydrogen, collapses under its own gravity. As the core gets hotter and denser, it eventually reaches the critical temperature and pressure needed to ignite nuclear fusion, and a star is born. It's a balance act. The outward pressure from fusion fights against the inward pull of gravity, creating a stable, shining object. A primordial dark star throws that entire textbook chapter out the window. Its formation begins not just with gas, but with a huge reservoir of dark matter. In the early universe, theorists believe the most likely candidate for this dark matter is a type of particle known as a WIMP, which stands for weakly interacting massive particle. As the name implies, these particles have mass and feel gravity, but they barely interact with normal matter or light. They mostly just pass right through it. However, they can interact with each other. This is where the magic happens. Inside a collapsing cloud of primordial gas, dark matter particles become gravitationally trapped, creating an incredibly dense core. When two WIMP collide, they can annihilate each other, converting their mass directly into energy according to Einstein's famous equation, E equals mc squared. This process releases a phenomenal amount of heat. Now, imagine this is happening not in a single event, but in a continuous, raging storm of collisions at the heart of the cloud. This energy source is fundamentally different from fusion. It's far more efficient and doesn't require the incredibly high temperatures and pressures that fusion demands. So, as the gas cloud tries to collapse further to form a conventional fusion-powered star, this intense, dark matter-powered heating provides a powerful outward pressure that halts the collapse. The cloud stabilizes not as a compact, fusion-driven star, but as a vast, puffy, and extraordinarily luminous ball of gas, centrally heated by dark matter annihilation. It's not a star in the nuclear sense. It's a completely new class of object, a gravitational trap that uses dark matter as its fuel. This mechanism allows it to grow to sizes that are simply impossible for any fusion-based star, becoming the first true giants of the cosmos. Now, let's shift our gaze from the ancient universe to the very heart of our own cosmic home, the Milky Way galaxy. At its center, 26,000 light-years from Earth, lies a confirmed monster, the supermassive black hole known as Sagittarius, a star. For decades, astronomers have studied its powerful gravitational grip, watching stars whip around it at breathtaking speeds. But what if this known Leviathan isn't the only massive object lurking in the galactic core? A growing body of evidence suggests there might be something else hiding in the shadows, an unseen companion whose subtle gravitational tugs are only just beginning to be understood, a potential dark star. The clues for this hidden giant come from the precise movements of objects orbiting Sagittarius, a star. While many stars follow predictable paths dictated by the black hole's immense gravity, a few exhibit tiny yet persistent anomalies in their orbits. It's as if an invisible hand is giving them an occasional, gentle nudge. After meticulously ruling out other explanations, like dense clouds of gas or clusters of smaller black holes, some scientists have proposed a truly fascinating possibility: a dark star. This wouldn't be a primordial giant from the early universe, but a more recent and equally bizarre type of object. Perhaps a degenerate star made of exotic matter, or a failed black hole with a structure we don't yet comprehend. The hypothetical properties of such an object are mind-bending. To exert the observed gravitational influence without being seen, it would need to be incredibly massive yet possess no detectable light emission. It could be a quark star, an ultra-dense body where the very protons and neutrons have broken down into a soup of their fundamental components. Or it might be a boson star, a hypothetical object theorized to be made up of dark matter particles themselves, acting as a single massive quantum entity. This dark star wouldn't be competing with Sagittarius, a star. Instead, the two would be locked in a slow, gravitational dance, a cosmic waltz of a visible titan and an invisible one, their combined forces subtly orchestrating the motions of everything around them. The search for this ghostly companion is one of the most exciting detective stories in modern astronomy. Researchers are using the world's most powerful telescopes, from the Keck Observatory in Hawaii to the Very Large Telescope in Chile, to track the motions of individual stars near the galactic center with unprecedented precision. Every slight wobble, every unexpected acceleration in a star's path is a potential clue. The upcoming 30-meter telescope and the extremely large telescope, with their revolutionary resolution, are poised to take this search to a whole new level, potentially allowing us to finally pinpoint the location and mass of this elusive object, confirming whether one of the universe's greatest secrets has been hiding in our own backyard all along. But our search for these cosmic ghosts isn't confined to the bustling centers of galaxies. To find the next candidate, we must venture into the deepest, most empty voids of the universe, the immense and nearly vacant space between galaxies. Here, drifting through the eternal cold and darkness, could be lone wanderers, rogue dark stars on an endless journey through nothingness. The very idea of a star existing in complete isolation from any galaxy challenges our conventional understanding of cosmic architecture. Stars are born in galaxies. They live, die, and recycle their materials within them. The notion of a star, especially one of immense mass, somehow being ejected entirely from its galactic home seems almost fantastical. Yet, the dynamic and often violent interactions within galaxies make it not just possible but probable. Dense star clusters or the chaotic environments near supermassive black holes can act as gravitational slingshots, flinging stars out into the intergalactic void at incredible speeds. These become hypervelocity stars, and while we have observed a few of these normal, shining exiles, it stands to reason that their dark and massive counterparts could have been ejected in the same way. The true challenge and the defining characteristic of a rogue dark star is its profound invisibility. Adrift in the emptiness between galaxies, there is no illuminating gas cloud for it to ignite, no nearby star to reflect its light, and no planetary system to betray its presence through transits. It emits no light, no radio waves, no X-rays. It is a perfect cosmic stealth object, a gravitational anchor in a sea of darkness. Without any electromagnetic signature, our telescopes, which are designed to collect light across all wavelengths, are essentially blind to it. So how could we ever hope to find such a perfectly hidden object? The answer lies not in light, but in the subtle warping of spacetime itself through a phenomenon called gravitational microlensing. Imagine this dark wanderer after millions of years of solitary travel. Its path happens to align perfectly between our telescope on Earth and a distant background star in another galaxy. As the dark star passes through this precise line of sight, its gravitational field will act like a lens, bending and focusing the light from that background star. From our perspective, the distant star will temporarily appear to brighten, flare up for a period of days or weeks, and then slowly fade back to its normal luminosity as the dark star moves out of alignment. This microlensing event is a tiny, fleeting signature, but it is a direct and undeniable measure of the object's mass. By carefully analyzing the duration and shape of the brightening curve, astronomers can deduce the mass of the lensing object, confirming the presence of something massive that itself gives off no light. Surveys like the Optical Gravitational Lensing Experiment, or OGLE, and future missions with the Nancy Grace Roman Space Telescope are actively scanning millions of stars in the hopes of catching these rare and telltale flashes. Each one is a potential clue, a brief signal from the darkness that might finally reveal one of these lonely titans on its endless journey through the void. Now consider a cosmic dance between partners, one we can see and one we cannot. Throughout the galaxy, many stars are born in pairs, orbiting a common center of gravity in what we call binary systems. These stellar duos are laboratories for understanding gravity and mass, but sometimes the visible star behaves in a way that defies all expectation, wobbling or accelerating as if tugged by an invisible partner. This is where we find some of the most compelling evidence for dark stars not as solitary monsters, but as hidden companions in plain sight. Take the case of a seemingly ordinary star hurtling through space. Astronomers can measure its velocity and plot its path with incredible precision. If that star is tracing a complex, wobbling orbit instead of a smooth, predictable line, it signals the gravitational pull of an unseen object. By applying the laws of physics pioneered by Kepler and Newton, scientists can then calculate the mass of whatever is doing the pulling. Sometimes that calculated mass is significant, yet absolutely nothing is there in any wavelength of light we can detect. This is the signature of a dark companion. One of the most famous historical examples of this phenomenon didn't involve a star but a pulsar. Pulsar B1913+16, known as the Hulse-Taylor binary pulsar, consists of two ultra-dense neutron stars orbiting each other. Its discovery provided the first indirect evidence for gravitational waves and earned a Nobel Prize. It proved that we can accurately diagnose a system based solely on its orbital mechanics. Today, astronomers are applying this same principle to systems where only one object is visible and the other remains a complete mystery. The observed star might be a main sequence star like our Sun, but its motion suggests it is locked in a gravitational embrace with a partner that has 5, 10, or even 20 times the mass of our Sun, yet emits no light whatsoever. What could this invisible partner be? It rules out the usual suspects. It's too massive to be a planet. If it were a neutron star or a standard black hole, we would often detect some form of emission, X-rays from accreted material or radio pulses. The absence of any such signal points toward something even more exotic. This dark companion could be a black hole so isolated and quiet that it's not actively feeding, making it effectively invisible. Or it could be something far stranger, like a theoretical quark star, an object so densely packed that it represents a state of matter between a neutron star and a black hole. The search for these systems is relentless. Projects like the European Space Agency's Gaia mission are creating an unprecedented three-dimensional map of our galaxy, precisely charting the positions and movements of over 1 billion stars. Within this immense dataset, astronomers are hunting for stars with those telltale, unexplained wobbles, the silent gravitational fingerprint of a dark partner. Each candidate system is a story waiting to be told, a cosmic mystery where the visible actor on stage is hinting at the presence of a hidden lead, whose nature could rewrite our understanding of what can exist in the vast stellar populations of the Milky Way. Now imagine a stellar nursery, a place of birth and chaos like the famed Orion Nebula. These colossal clouds of gas and dust are the cradles of new stars where gravity slowly pulls matter together until nuclear fusion ignites. But what if hidden within these vibrant clouds, masked by the very gas that gives them form, lies a different kind of heart, not a brilliant young star, but a silent, dark anchor? This leads us to the intriguing possibility that certain dense nebula cores might not be nurturing protostars, but instead concealing fully formed dark stars whose presence could dramatically alter the entire life cycle of the cloud. The conventional process of star formation is a delicate ballet. Within a nebula, pockets of gas collapse, growing denser and hotter until they become protostars. Their eventual ignition blows away the remaining gas, halting further growth and lighting up the cloud. But astronomers observing regions like the Orion Molecular Cloud Complex have sometimes detected puzzling gravitational signatures, areas where the gas appears to be swirling too rapidly, as if orbiting an unseen, massive object at the core. The calculated mass for this hidden anchor can be substantial, sometimes many times that of our Sun, yet there is no corresponding infrared or radio source to account for it. It's as if the vibrant nebula itself is acting as a cloak, hiding a massive secret within its dusty folds. A dark star nestled in such an environment would be a cosmic paradox, an object that prevents the very star formation happening around it. How its immense gravitational pull would certainly draw in gas and dust from the surrounding cloud. However, without a fiery surface or intense radiation, it wouldn't provide the heat and stellar winds that normally help regulate the collapse of nearby material. Instead, it would act as a gravitational vacuum, creating chaotic and powerful turbulence within the cloud. This could either trigger a burst of frantic star formation in some areas by compressing gas waves, or, more likely, suppress it entirely by sucking away the raw material needed for new stars to be born, effectively starving the nursery. The hunt for these hidden cores is incredibly difficult. Astronomers must rely on indirect methods, using radio telescopes to map the velocities of gas molecules like carbon monoxide. By analyzing these movements, they can create a gravitational map of the cloud, pinpointing locations where the motion of the gas suggests a concentrated mass that remains completely dark. Each candidate is a story of contradictory forces, a place of potential birth overshadowed by a mysterious, invisible presence. Confirming one would revolutionize our understanding of nebulae, suggesting they are not only star-forming factories but also potential hiding places for some of the universe's most enigmatic and massive objects. For decades, quasars have been the crown jewels of extreme astrophysics, the most luminous and energetic objects in the entire universe. We've been told their story. At the heart of a distant galaxy, a supermassive black hole, weighing in at millions or even billions of times the mass of our Sun, is actively feeding. As vast quantities of gas spiral inward in a superheated accretion disk, friction and gravitational forces release a mind-boggling amount of energy before the material crosses the event horizon, vanishing from our universe forever. This model is elegant, powerful, and has served as the fundamental explanation for quasars and their cousins, active galactic nuclei, for over half a century. But what if we've been misinterpreting the cosmic data? What if the engine at the heart of some of these brilliant beacons isn't a black hole at all, but something even more bizarre, a dark star of unimaginable proportions? The idea isn't as far-fetched as it might seem. It begins with a simple but profound question: how can we truly be certain the central object is a black hole? We cannot see the event horizon itself. Our evidence is entirely indirect, based on the incredible energy output, the rapid orbital speeds of nearby stars, and the compact size of the energy source. A supermassive dark star could, in theory, mimic these signatures with astonishing accuracy. Imagine an object with a mass equal to a supermassive black hole, but one that has a physical surface rather than an event horizon. This surface could be made of exotic matter, perhaps a condensate of dark matter particles or a degenerate state we haven't yet discovered, that is incredibly dense and capable of supporting its own immense weight against total collapse. The energy output, the very thing that makes a quasar visible across the universe, could be explained through a different mechanism. Instead of gravitational energy released by infalling matter just outside an event horizon, a dark star might generate its power through the annihilation of dark matter particles within its own structure. If this hypothetical object existed in a region swimming with dark matter, perhaps at the very center of a galaxy where dark matter is thought to be most dense, it could provide a continuous, incredibly potent fuel source. The energy released from this annihilation process could easily rival the ferocious output of an accretion disk, creating a brilliant beacon that looks for all intents and purposes like a classic quasar. This alternative theory creates significant tension with established astrophysical models, particularly around the process of accretion. A black hole is simple, it consumes everything. Matter falls in, energy comes out from just outside the point of no return. A dark star with a surface presents a complex problem. What happens when infalling matter actually hits that surface? Would it create a titanic explosion, a splash of radiation that looks different from the smooth energy curve of an accretion disk? Or would the exotic nature of the surface allow it to absorb matter without a violent release of energy, somehow channeling it into the dark matter annihilation process? These questions strike at the heart of our understanding of high-energy physics and force us to reconsider every assumption we make when we look at the brilliant core of a distant galaxy. The most compelling evidence for the black hole model has always been the incredible compactness of these energy sources. Using a technique called reverberation mapping, astronomers have measured the size of the central engine in some active galaxies and found it to be smaller than our solar system, yet pouring out more light than 1 trillion stars. This seems to demand an object that is both tiny and unimaginably massive, a description that fits a black hole perfectly. However, some models of supermassive dark stars, particularly boson stars, predict they could also be incredibly dense and compact, potentially matching these size constraints. Distinguishing between the two would require detecting a subtle but crucial difference: the absence of an event horizon. Future gravitational wave observatories and next-generation telescopes designed to study the immediate environment of these monsters might one day detect the faint echo of matter striking a hard surface, a discovery that would shatter the standard model and open a thrilling new chapter in our quest to understand the true rulers of the cosmic dark. While quasars challenge our present understanding of cosmic engines, another candidate takes us back to the very beginning, offering a glimpse into the universe's deepest past. Imagine if we could find an object that never truly died, a fossilized relic from the first chapter of cosmic history, preserving within it the pristine conditions of the infant universe. This isn't a frozen chunk of rock or ice, but a celestial time capsule of almost unimaginable mass and age, a surviving primordial dark star. Most of those first monstrous dark stars are thought to have collapsed long ago, their dark matter fuel exhausted, seeding the early universe with the first supermassive black holes. But what if the conditions were just right for one to avoid that fate? In a region with an unusually dense and long-lasting reservoir of dark matter, a primordial dark star might have stabilized. Instead of collapsing, it could have entered a state of suspended animation, cooling and darkening over billions of years, yet still retaining its immense mass and strange, exotic structure. It would no longer shine with the fierce brilliance of its youth, but it would still be there, a dormant giant hiding in plain sight within an ancient corner of a modern galaxy. Discovering such an object would be the astronomical equivalent of finding a living dinosaur. It would be a direct, untouched sample of the universe's first billion years. The composition of its core would be a Rosetta Stone for particle physicists. By studying its properties, we could finally determine the true nature of those early dark matter particles, their mass, their interaction cross-section, and how they behaved in the extreme environments that simply don't exist anywhere in the present-day universe. All of this information is crucial for scientists trying to detect dark matter directly in underground labs or create it in particle colliders. A surviving dark star would tell them exactly what to look for. Furthermore, the distribution of these relics would paint a detailed map of the early cosmos. The presence of a time capsule dark star in a particular part of a galaxy would indicate where the densest clumps of primordial dark matter were located. This would allow us to test and refine our models of how the universe evolved from a smooth soup of particles into the structured web of galaxies and dark matter halos we see today. It would provide a critical check on our entire cosmological timeline, offering tangible evidence from an era that is currently only understood through theory and the faint afterglow of the Big Bang. The search for these ancient survivors is a painstaking process of elimination. Astronomers would look for a massive, compact object that exerts a powerful gravitational pull, perhaps influencing the orbits of nearby stars or causing microlensing events, but one that is completely, utterly dark across the entire electromagnetic spectrum. It would have no planetary nebula, no accretion disk, no stellar companion from which it steals material. It would be a gravitational signal and nothing more, a silent witness to the dawn of time, waiting patiently in the darkness for us to finally develop the tools and the ingenuity to recognize it for what it is. Finding just one would open a window into a lost epoch, giving us a first-hand account of the universe's mysterious and powerful beginnings. Shifting our focus from the silent, gravitational ghosts to the most violent explosions in the cosmos, we enter the realm of gamma-ray bursts. These are not gentle flickers of light. They are the universe's most powerful detonations, capable of releasing more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. For decades, astronomers have categorized them into two types: long bursts, believed to be the death cries of massive stars collapsing into black holes, and short bursts, thought to be the collisions of ultra-dense neutron stars. Yet, a small but persistent fraction of these events defies all classification. They don't fit the profile, they don't come from the expected environments, and their energy signatures are just wrong. These outliers are the cosmic cold cases of high-energy astrophysics, and one compelling suspect is the dark star. The key to this dark star connection lies in the theoretical process we touched on earlier: dark matter annihilation. Imagine the core of a dense, massive dark star, a roiling cauldron where dark matter particles are constantly colliding and annihilating each other. Under normal circumstances, this process might be stable, providing a steady heat source. But what if something disrupts that delicate balance? A close encounter with another massive object, a sudden infusion of new dark matter, or an internal phase transition could trigger a runaway reaction. The annihilation rate could spike catastrophically, leading to a titanic release of energy not as gentle heat, but as an overwhelming firestorm of gamma radiation, a burst. This model provides an elegant explanation for those strange, unclassifiable gamma-ray events. A dark star undergoing such an annihilation-induced collapse wouldn't be found in a busy star-forming region like a long burst, nor would it be part of a binary system like a short burst. It would be an isolated event, a brilliant flash originating from a seemingly empty patch of space, with an energy profile that doesn't match the known physics of collapsing stars or colliding neutron stars. The afterglow, the fading light that follows the initial blast, would also look different. Instead of the signature of expanding stellar debris or a kilonova's rich brew of heavy elements, it might fade in a unique way, leaving behind a telltale and ultimately dark remnant. One of the most famous mysteries in this field is the event known as GRB 070614. Detected in 2007, this incredibly powerful burst lasted for over 100 seconds, which should firmly place it in the long burst category caused by a supernova. But when astronomers pointed their best telescopes at the location, they found nothing. No host galaxy, no trace of an accompanying supernova explosion, no evidence of a stellar nursery. It was a ghost burst appearing to come from the middle of a cosmic void. For years, it has remained an enigma. A dark star undergoing a final, violent paroxysm of dark matter annihilation in the emptiness between galaxies fits the profile of this and other orphan bursts perfectly. It's a solitary monster dying alone in the dark, its final scream echoing across the universe as a burst of light we are only just beginning to interpret. Moving beyond the bustling galactic disk and the lonely voids between galaxies, we come to a vast spherical shroud that envelops every galaxy like a ghostly crown, the galactic halo. This immense region is not empty. It's filled with a sparse population of ancient stars, globular clusters, and most intriguingly, a tremendous amount of unseen mass. For decades, the nature of this halo mass has been one of astronomy's most persistent puzzles, often attributed to a smooth distribution of dark matter. But what if a portion of this missing mass isn't a featureless cloud of particles, but takes the form of massive, discrete objects, dark stars anchored within the halo itself? The evidence for this unseen halo mass is rock solid. We observe stars and gas clouds at the far edges of galaxies orbiting at speeds that are simply too fast. According to the laws of gravity, these outer regions should be moving much more slowly if the only gravitational pull came from the visible mass of stars and gas in the galactic disk. The only explanation is that they are being whipped around by the gravitational attraction of a massive, invisible component that extends far beyond the luminous edge of the galaxy. While the leading theory points to a halo of cold dark matter, the possibility remains that some fraction of this mass could be locked up in macroscopic objects, and dark stars are a prime candidate. These wouldn't be the fiery, dark matter-powered giants of the early universe. A halo dark star would more likely be a cold, dead relic, a black hole of stellar or intermediate mass, or an exotic object like a quark star that was flung out of the chaotic galactic disk long ago and found a stable orbit in the sparse halo. Over billions of years, it would have cooled completely, emitting no light and having no accretion disk to feed on, making it the ultimate stealth object. Millions of these dark remnants could be drifting through the galactic halo, collectively accounting for a significant portion of the gravity that binds the galaxy together. So how do we find a single, perfectly black object lost in the incredible volume of a galactic halo? The primary tool is once again gravitational microlensing, but on a truly colossal scale. International surveys like the optical gravitational lensing experiment meticulously monitor hundreds of millions of stars, not just in our own Milky Way, but in nearby satellite galaxies like the Large and Small Magellanic Clouds. The genius of this method is that the dark halo objects of our own galaxy would act as lenses for the background stars of these other galaxies. If a dark star in the Milky Way's halo passes directly between us and a star in the Large Magellanic Cloud, it will cause a characteristic temporary brightening of that distant star's light. The signature of such an event is distinct. The duration of the brightening tells us the mass of the lensing object. A lensing event caused by a planet might last hours. One caused by a stellar mass dark star would last days or weeks. By statistically analyzing the number and duration of these microlensing events, astronomers can actually take a census of the invisible population inhabiting our halo, estimating both their masses and their abundance. This data provides a crucial reality check, testing whether such objects could indeed account for any of the galaxy's missing mass, or if the halo must be composed of something more fundamental. Another powerful method involves studying the very motions that revealed the halo's mass in the first place. While the overall rotation curve of a galaxy tells us the total mass of the halo, finer details can hint at its structure. If the dark mass were partly made of discrete objects like dark stars, it wouldn't be perfectly smooth. This clumpiness would create slight variations in the velocity dispersion of the halo stars, meaning the random motions of stars within the halo would show subtle anomalies compared to what you'd expect from a perfectly smooth dark matter distribution. Detecting this requires exquisitely precise measurements of the motions of countless individual halo stars, a task perfectly suited for the Gaia Space Observatory. As Gaia continues to chart the proper motions of stars with unparalleled accuracy, it may eventually reveal the faint gravitational fingerprint of these massive invisible halos within the halo, finally bringing the darkest residents of our galaxy into the light. Up until now, we've explored dark stars as consumers of dark matter, using it as a revolutionary fuel source. But what if we've got the story backwards? A truly mind-bending theory proposes that these cosmic enigmas might not just be using dark matter, they could actually be creating it. Imagine a celestial factory, not of light and heat, but of the universe's most mysterious substance. This concept turns the entire narrative on its head and suggests dark stars could be the hidden engines responsible for the dark matter we detect all around us. To understand how this might work, we need to venture into the cutting edge of theoretical particle physics. Our standard model of particles is incredibly successful, but it's incomplete. It doesn't include a candidate for dark matter. Physicists have proposed numerous extensions to the model, many of which include whole new families of particles. Some of these theories suggest that under the extreme conditions found in nature, conditions far more intense than anything we can create in a particle collider, certain known particles could transform or decay into dark matter particles. The core of a dark star, with its immense density, pressure, and potentially unique quantum fields, could provide the perfect crucible for this exotic alchemy. Think of it like a nuclear reactor, but infinitely stranger. In an ordinary star, atomic nuclei fuse together to create new, heavier elements. In this dark matter factory model, the intense environment could be causing fundamental particles to transmute. For instance, theories involving asymmetric dark matter suggest that an imbalance in the number of particles and antiparticles in the early universe, similar to the process that gave us more matter than antimatter, could be ongoing in these extreme environments. The dark star's core could be continuously generating a surplus of dark matter particles, which then stream out into the cosmos, replenishing the universal supply. This idea has profound implications for one of cosmology's biggest puzzles, the missing satellites problem. Our simulations of the universe based on the standard cold dark matter model predict that our Milky Way galaxy should be surrounded by thousands of small dwarf satellite galaxies. Yet we only observe a few dozen. If dark matter were being produced and ejected from objects within galaxies, it could change how dark matter halos form around smaller structures, potentially explaining why we don't see as many small galaxies as the models suggest. The distribution of dark matter might not be a simple relic of the Big Bang, but a dynamic, ongoing process with dark stars acting as hidden wellsprings. The challenge, of course, is testing this incredible hypothesis. We cannot peer inside these objects. Instead, astroparticle physicists look for the consequences. They run sophisticated computer models to simulate the proposed particle interactions within a dark star's core, predicting the types and energies of any secondary particles that might be produced alongside the dark matter. They then scour data from neutrino observatories and gamma-ray telescopes, searching for anomalous signals that cannot be explained by any known astrophysical process. A specific, unexpected pattern of radiation emanating from a region of concentrated gravity could be the first hint that we've found not just a consumer, but a creator, a permanent engine working in the shadows to shape the very fabric of our universe. Now, let's dive into one of the most subtle yet compelling lines of evidence in this entire search. A signal not of light, but of nearly massless particles that barely interact with anything at all, neutrinos. Flowing through you and everything around you at nearly the speed of light are trillions of these ghostly particles every second, originating from the sun, from our atmosphere, and from distant cosmic events. For the most part, they pass through the entire Earth without leaving a trace, but occasionally, just one in a million, one will interact with matter and we can detect it. Massive, hypersensitive observatories like IceCube, buried deep in the Antarctic ice, are designed to catch these rare interactions, building a map of the universe not in light, but in these elusive messengers. And within the torrent of data they collect, there are anomalies, unexplained fluxes of neutrinos that seem to point back to regions of empty space. One provocative explanation for these mysterious signals is the dark star, not as a source of light, but as a powerful and unique neutrino emitter. To understand why a dark star could be such a potent neutrino factory, we need to look at its proposed engine, dark matter annihilation. When two dark matter particles like WIMP collide and annihilate, they don't just vanish. Their mass is converted into energy, which must manifest as other particles. The specifics depend on the exact nature of the dark matter, but many leading theoretical models predict that these annihilation events will produce a standard model shower, a burst of particles that includes protons, electrons, gamma rays, and crucially, neutrinos. In most environments, this would be a secondary effect, but inside a dark star where annihilation is the primary, continuous process, the production of neutrinos wouldn't be a side effect, it would be a fundamental and constant output. The star would essentially be a dedicated neutrino generator, broadcasting its presence across the galaxy in a language of neutral particles. This creates a potential fingerprint, a way to distinguish a dark star's signal from every other neutrino source in the sky. Consider a supernova. It produces a tremendous but brief flash of neutrinos in a specific energy range. A blazar, a type of active galaxy, might produce a constant stream of neutrinos correlated with its gamma-ray emissions. A dark star's neutrino signature would be different. It would be a steady, unfluctuating point source of neutrinos, emanating from a location that appears completely dark in every telescope. Furthermore, the energy spectrum of those neutrinos, the distribution of their energies, would carry the specific imprint of the dark matter particles that created them. It would be a direct readout of the physics happening in the core, something no other astronomical object could easily mimic. This is where detectors like IceCube become the ultimate dark star hunters. IceCube doesn't see neutrinos directly. Instead, it monitors a cubic kilometer of pristine Antarctic ice for a faint flash of blue light called Cherenkov radiation. This flash occurs on the incredibly rare occasion that a neutrino, after traveling for millions of years, finally collides with an atom in the ice. By meticulously reconstructing the direction and energy of the incoming neutrino from the properties of this light, scientists can trace a path back to its origin in the sky. They are already doing this to identify known sources, like the blazar TXS 0506 plus 056, which was identified as a neutrino source in 2018. The next step is to look for those steady, bright points of neutrino emission that have no optical, radio, or gamma-ray counterpart. Several candidate events have already put this idea to the test. There have been instances where IceCube has detected a cluster of neutrinos, a hotspot, in the neutrino sky coming from a specific location. Astronomers then swing every other telescope they have to that same patch of space, searching for anything that could be the culprit: a flaring black hole, a distant supernova, a pulsar. In a handful of cases, they have found absolutely nothing. The coordinates point to a void, a seemingly empty depth of space. Yet the neutrinos keep coming. While these could be statistical flukes or the signatures of entirely new phenomena, they align perfectly with the prediction for a stable, isolated dark star, continuously annihilating dark matter and broadcasting its existence through a silent scream of neutrinos. Each unexplained point source is a beacon, a potential coordinate for a hidden giant, waiting for its neutrino whisper to be fully understood. But our journey into the deepest possibilities of dark stars must venture beyond particles and gravity into the very fabric of space-time. To find perhaps the strangest candidate of all, we must consider that the universe itself might be woven from imperfections, cosmic scars from its initial hyper-energetic birth. These are not objects in the traditional sense, but flaws in the geometry of reality known as topological defects. And among the most extreme of these theoretical structures are cosmic strings, unimaginably thin cracks in space-time that may have formed as the fundamental forces of nature froze into their current state during the universe's rapid cooling after the Big Bang. A cosmic string is a mind-bending concept. Think of it as a one-dimensional flaw in the cosmos, a wrinkle in the fabric of space-time that possesses immense density. It would be thinner than a proton, yet a single inch of it could weigh more than Mount Everest. These strings, if they exist, would stretch across the entire universe, vibrating and oscillating over eons. And where these infinitesimally thin, ultra-dense lines of pure energy intersect and cross, something incredible could happen. The gravitational pull at the junction of two or more cosmic strings would be so phenomenally strong that it could instantly gather and trap any nearby matter and dark matter, potentially seeding the instantaneous formation of a dark star of simply unfathomable mass. This wouldn't be a star that forms over millions of years from a collapsing gas cloud. This would be a star that snaps into existence, fully formed, at a point where the underlying geometry of the universe is fundamentally flawed. The resulting object, a cosmic string-anchored dark star, would be unlike any other we've discussed. Its stability would be guaranteed not just by internal processes, but by the cosmic string itself, which acts as a permanent, unbreakable tether to the fundamental structure of reality. It would be a fixed point in the cosmos, an eternal landmark around which galaxies and galactic clusters might eventually form. The influence of such an object on the large-scale structure of the universe would be profound. We see that galaxies are not scattered randomly. They form a vast cosmic web of filaments and nodes with huge voids in between. The prevailing theory is that this web was spun from the gravitational seeds of dark matter fluctuations in the early universe. But what if some of the most massive nodes, the places where multiple galactic superclusters converge, are not just random dark matter halos? What if they are anchored by these primordial monsters, these dark stars born at the intersection of space-time defects? Their immense fixed gravitational wells would act as the ultimate attractors, pulling in matter over billions of years and dictating the flow of the cosmic web on the very largest scales. The search for evidence of such a wild idea is, as you might expect, incredibly indirect. Astronomers would look for anomalies in the cosmic microwave background, the afterglow of the Big Bang. The immense gravity of a cosmic string would leave a unique, sharp discontinuity in this background radiation as it passed through the universe. Furthermore, the gravitational lensing effect of a fixed, ultra-massive object would be distinctive, potentially creating multiple, sharp images of distant quasars in a pattern unlike the smoother lensing caused by a galaxy cluster. While no definitive evidence exists today, the mere possibility that the largest structures we see in the sky could be organized around these invisible, stable giants themselves tied to the cracks in creation is a testament to how deeply strange and wondrous our universe may truly be. Now we journey to a pivotal moment in cosmic history, a transition so profound it shaped the entire future of the universe, the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was a tranquil, dark sea of neutral hydrogen gas. Then something happened. An intense, pervasive radiation flooded the universe, stripping electrons from these hydrogen atoms and ionizing the entire intergalactic medium, making space transparent to ultraviolet light for the first time. This event, reionization, is a cornerstone of our cosmic timeline, but the source of that transformative radiation has long been a subject of intense debate. The usual suspects are the first quasars and the brilliant, short-lived population 3 stars. But what if there was another, even more powerful actor on the stage? Enter the dark star, offering a radical solution to the reionization enigma. To appreciate the scale of this puzzle, consider the energy required. Ionizing all the hydrogen in the young universe wasn't a task for a few bright lights. It demanded a colossal and sustained output of high-energy ultraviolet photons. For decades, cosmologists have pointed to 2 primary sources. The first is quasars, powered by supermassive black holes gobbling up vast amounts of gas. The second is population 3 stars, the universe's first generation of stars. These were behemoths hundreds of times more massive than our Sun, burning ferociously hot and bright, and flooding their surroundings with ionizing UV radiation before dying in spectacular supernova. The problem is, there's a growing tension between theory and observation. Our best models suggest there might not have been enough of these objects formed early enough to complete reionization by the time we know it happened. The cosmic clock, as measured by the Planck satellite and other observatories, doesn't quite match the story we've been telling. We're missing a key piece of the puzzle. This is where the primordial dark star emerges as a game-changing contender. Recall their staggering properties. A single dark star could outshine an entire galaxy. But it's not just about raw luminosity, it's about the type of light they emit. The dark matter annihilation process at their core is theorized to produce a much higher proportion of high-energy, ionizing photons compared to even the hottest fusion-powered stars. A quasar's radiation is concentrated from a tiny, intense accretion disk, while a population 3 star's light comes from its searing surface. A dark star's energy, generated throughout its vast interior, could have created a far more effective and pervasive ionizing field. A few hundred of these dark giants could have done the work of millions of smaller, conventional stars, flooding the primordial hydrogen fog with ionizing radiation and punching transparent bubbles into the cosmos at a remarkably rapid pace. This alternative narrative elegantly addresses several sticky problems. The timing of reionization becomes less of an issue. Population 3 stars lived fast and died young, exploding quickly and shutting off their ionizing output. Quasars require fully formed supermassive black holes which take time to build. Dark stars, however, could have ignited incredibly early, when the universe was only 100 or 200 million years old, and crucially, they could have been incredibly long-lived. Stable dark stars might have shone for millions of years, providing a steady, persistent source of ionizing radiation that could have begun the process earlier and sustained it for longer than the flickering bursts of light from short-lived supernova or intermittent quasars. This sustained push might be exactly what's needed to reconcile our models with the observed timeline. The most compelling evidence for this idea will come from the next generation of space telescopes. The James Webb Space Telescope is already peering back to this era, searching for the fingerprints of the first light sources. If the standard model is correct, we should see a universe gradually twinkling to life with countless small, hot stars. But if Webb and future observatories like the Nancy Grace Roman Space Telescope instead detect a few inexplicably, impossibly bright and giant objects from this incredibly early time, objects that defy the physics of nuclear fusion, it could be the first direct hint that dark stars were the true architects of the clear, transparent universe we inhabit today. They wouldn't just be hidden monsters, they would be the cosmic lighthouses whose brilliant radiation carved out the visible universe, making everything we see possible. While our eyes are trained on the heavens for flashes of light and our detectors listen for whispers of neutrinos, an entirely new sense has opened up for exploring the cosmos, the ability to hear the vibrations of spacetime itself. Gravitational wave astronomy has revolutionized our understanding of the universe's most violent events, from the mergers of black holes that send ripples through the fabric of reality to the collisions of neutron stars that shine with light and gravitational waves in unison. But within the growing library of these cosmic rumbles, detected by facilities like LIGO and Virgo, there are events that don't quite fit the established patterns. Some collisions are too quiet, too clean, or have a signature that is just slightly off. This has led theorists to ask a thrilling question: could some of these unexplained ripples be the death spirals of dark stars? To understand what makes a dark star merger unique, we first need to appreciate how LIGO and Virgo identify what they're hearing. When two black holes spiral inward and collide, the gravitational wave signal has a very specific character. It's often described as a chirp, a rapid increase in the frequency and amplitude of the wave as the objects get closer and faster. culminating in a final, violent ring-down as the single new black hole settles into its stable form. The precise shape of this signal tells scientists the masses of the objects, their spins, and even their distance from Earth. Neutron star mergers produce a different kind of signal, typically at higher frequencies, and are often accompanied by a brilliant electromagnetic flash across the spectrum, known as a kilonova. A merger involving two dark stars would write a completely different song on the fabric of spacetime. The key difference lies in the nature of the object's surfaces. A black hole has no surface, it has an event horizon, a point of no return from which even the gravitational wave signal cannot escape after the merger. The collision is, from a gravitational wave perspective, a very clean event. Now, imagine if one or both of the merging objects had a physical surface, perhaps made of exotic matter like a quark-gluon plasma or a condensate of dark matter particles. As these two ultra-dense objects spiral together in the final moments before collision, their surfaces would not simply vanish. They would stretch, deform, and potentially even touch before the final merger. This contact would dramatically alter the gravitational wave signal. Instead of a clean chirp ending in a sharp ring-down, the signal would be messier. The interaction of the two surfaces would create additional vibrations and resonances in the gravitational waves, a kind of friction or turbulence in spacetime that would be absent in a black hole merger. Furthermore, the final act itself would be different. If the merged object collapsed into a black hole, the ring-down would be one signature. But if it instead formed a new, larger dark star, the ring-down would be noticeably quieter and longer, as the energy dissipates differently through an object with structure rather than being swallowed by an event horizon. The data from observatories like LIGO already contain events that have given scientists pause. One of the most famous is GW190521, an event detected in May of 2019. The initial analysis suggested it was the merger of two black holes, but one with a final mass that placed it squarely in what's known as the mass gap. This is a theoretical range between the heaviest possible neutron stars and the lightest possible black holes where we don't expect to find objects. The event was unusually quiet for its mass, and some analyses have suggested its gravitational wave signature had subtle features that don't perfectly align with a standard black hole merger. While not conclusive, it serves as a prime example of the kind of anomaly that could one day be reinterpreted as something far more exotic. The hunt for these exotic signatures is a meticulous process of subtraction and comparison. Astronomers run millions of computer simulations, modeling the gravitational waves that would be produced by every conceivable type of merger, from black holes and neutron stars to more theoretical objects like boson stars, quark stars, and other dark star candidates. They then take the real data from LIGO and Virgo and see which template provides the best statistical fit. It's like having a vast library of musical notes and trying to find the sheet music that best matches a mysterious recorded chord. An event that is a poor fit for all the standard templates but an excellent fit for a dark star model would be a monumental discovery. Future upgrades to gravitational wave observatories like the planned space-based LISA mission will open an entirely new low-frequency window onto the universe. This will allow us to hear the mergers of supermassive objects, the very kinds of dark stars that might be hiding in galactic centers. A collision between two such behemoths would create a gravitational wave tsunami, a low rumble that could last for months, potentially carrying the unmistakable signature of exotic physics. Each unexplained ping on the gravitational wave network is a potential clue, a vibration that might not be from a simple black hole, but from something whose true nature has remained hidden in the dark until now. We now turn our attention to some of the most enigmatic structures in the universe, the ghostly, almost transparent galaxies known as ultra-diffuse galaxies. These cosmic apparitions, like the famous Dragonfly 44, are the size of the Milky Way but contain barely 1% of its stars. They are vast, wispy clouds of stellar light, and according to the laws of gravity, they shouldn't exist at all. Their stars are so few and far between that the galaxy's own rotation should tear them apart. Yet they are stable, serene, and enduring. The only explanation is that they are held together by an immense, unseen gravitational force, a halo of dark matter so massive it defies all conventional understanding of how galaxies form. This presents a stunning paradox, a galaxy that is almost all halo with almost no galaxy inside it. But what if the heart of this darkness isn't a smooth, featureless cloud? What if, at the very center of these ghostly systems, lies a singular, monstrous anchor, a dark star of unprecedented mass? The stability of an ultra-diffuse galaxy is its greatest mystery. In a normal spiral galaxy, the visible disk of stars and gas provides a significant portion of the gravitational glue that holds everything together. In these faint giants, there is simply not enough visible matter to account for their cohesion. Their stars move at velocities that should send them flying off into the void, yet they remain bound in a stable orbit. This points to a central gravitational source of incredible power, something that can keep billions of stars in check across a vast volume of space. A supermassive black hole is the obvious candidate, but there's a problem. These galaxies show no signs of the energetic activity that typically surrounds a feeding black hole. There are no X-ray jets, no radio lobes, no accretion disk. The center is as quiet and dark as the outer regions. This silence is what makes the dark star hypothesis so compelling. A massive black hole that is completely dormant and isolated is one possibility. But another is an object we've never classified, a dark star that never emitted light in the first place, acting as a pure gravitational anchor. This dark star would be a different breed from the primordial ones, formed not in the early universe but perhaps much later through the direct collapse of a dense knot of dark matter within the galaxy's halo. This object would be a gravitational singularity in its own right. Its purpose wouldn't be to shine or to power a quasar, but simply to be. Its immense mass, which could range from hundreds of thousands to millions of solar masses, would provide the central point around which the entire galaxy organizes itself. The surrounding halo of dark matter would be densest in its immediate vicinity, creating a steep gravitational well that keeps even the farthest flung stars in a stable, orderly rotation. This would explain the galaxy's bizarre properties in one elegant stroke. The high mass-to-light ratio comes from the dark star and its associated dark matter, while the lack of any central engine emission is because the dark star, by its very nature, does not accrete matter or produce light in a conventional way. It is the ultimate dark heart. The search for evidence of these central dark stars is a task of immense subtlety. With the core of an ultra-diffuse galaxy being so faint to begin with, astronomers cannot look for the telltale wobbly motions of stars right next to the central object, as we can with Sagittarius, a star in our own galaxy. Instead, they must model the overall rotation curve of the entire galaxy with exquisite precision. They create sophisticated computer simulations, plugging in different models for the central mass, a point-like object versus a more spread-out distribution of dark matter. A model that includes a compact, supermassive dark star at the center often provides a better fit to the observed stellar motions than a model where the dark matter is perfectly smooth. It's a gravitational signature written in the slow, grand motions of millions of stars, a signature that hints at a silent titan holding the entire ghostly structure together against the forces that would otherwise tear it asunder. Finding one would not just solve the mystery of these dark galaxies, it would reveal an entirely new class of celestial object, one that governs not through light but through gravity alone. While our gaze has been fixed on the grandest scales of galaxies and the earliest moments of time, the influence of these dark giants might also be felt much closer to home in the delicate architectures of planetary systems. We now know that planets are not unique to our solar system. They are commonplace orbiting stars throughout the galaxy. With thousands of exoplanets discovered, we've begun to catalogue a stunning diversity of worlds, from hot Jupiters orbiting blisteringly close to their suns to frozen super-Earths in distant, dark orbits. Yet within this vast catalogue, there are systems whose precise arrangements defy our standard models of planetary formation. Their orbits are slightly off-kilter, their resonances are not quite perfect, or their entire structure seems precariously balanced. To explain these cosmic irregularities, astronomers must look for an external sculptor, a hidden hand that has gently, or not so gently, tugged at these systems. One of the most compelling and unsettling possibilities is that a dark star passed through their neighborhood long ago. Consider a system like TRAPPIST-1, a fascinating red dwarf star located about 40 light-years away. It is famous for hosting 7 roughly Earth-sized planets, all orbiting closer to their star than Mercury does to our Sun. What makes this system so intriguing for astronomers is its remarkable orbital resonance. The planets' orbits are synchronized, their orbital periods forming neat ratios with one another. This delicate gravitational dance suggests a relatively calm and orderly formation history. However, minute irregularities in their transits, the tiny dimming of the star's light as each planet passes in front of it, hint that their orbits might not be perfectly aligned or precisely circular. While tidal forces from the star can explain some of this, another potential explanation is the gravitational influence of a massive, unseen object that brushed past the system millions of years ago, a gravitational encounter that left a faint but lasting imprint on the planet's path. The mechanics of such an encounter are both simple and profound. A dark star, perhaps a cold stellar mass black hole or a rogue brown dwarf that failed to ignite, drifting silently through interstellar space. Its path takes it through the outer reaches of a young planetary system, far beyond the orbit of its outermost planets. Even at a distance of hundreds of astronomical units, far too distant to be seen or to disturb the system's stars significantly, its immense gravitational pull acts like a deep gravitational tide. As it passes, it exerts a gentle but persistent tug on every planet, comet, and asteroid in the system. For the inner planets, the effect might be minuscule, a slight perturbation. But for the outer planets, or for vast reservoirs of icy bodies like a distant Oort cloud, the effect can be dramatic, potentially altering orbital eccentricities, tilting orbital planes, or even flinging smaller objects inward in a cascade of disruption that can last for eons. The evidence for this would not be a single smoking gun, but a pattern of anomalies across multiple systems. Astronomers would search for a specific signature, exoplanet systems that are otherwise stable but possess 1 or 2 outer planets on unusually eccentric or inclined orbits, acting as gravitational signposts pointing to a past encounter. Alternatively, a system might show an unexpected abundance of hot, rocky planets or a high rate of comet impacts, suggesting that a distant reservoir of icy bodies was destabilized by a passing mass, sending a shower of material toward the inner system. By running sophisticated computer simulations that model the gravitational effects of a flyby, scientists can work backwards. They can input the current orbital parameters of a puzzling system like TRAPPIST-1 and let the simulation run in reverse, testing whether the introduction of a dark star of a specific mass and trajectory could sculpt the system into its present-day configuration. This search is a testament to the interconnectedness of the cosmos, a silent, invisible wanderer on a journey that may have begun in the chaotic heart of the galaxy, can travel for billions of years before its path briefly intersects with a fledgling family of worlds. Its passage, lasting perhaps a few thousand years, a mere blink in cosmic time, can leave a permanent signature, a subtle fingerprint of its mass and its path etched into the orbits of planets. It suggests that the history of a planetary system is not written solely by its star, but can be edited by the dark, silent ghosts passing through the interstellar night, their unseen gravity writing chapters in the lives of worlds we are only just beginning to discover. But what if the boundary between a dark star and a black hole isn't as absolute as we think? To explore our next candidate, we must venture beyond classical physics and into the bizarre quantum realm, where the very rules of gravity and reality are rewritten. This leads us to a theoretical construct so strange it challenges our definitions of both stars and singularities: a quantum dark star. Unlike a black hole, which is defined by its inescapable event horizon, a quantum dark star is theorized to be an ultra-dense object that halts its collapse just shy of that point of no return, thanks to the bizarre and repulsive effects of quantum mechanics at an unimaginable scale. The core idea stems from a major unsolved problem in physics, uniting Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. At the heart of a collapsing star, both regimes should theoretically meet, but our current models break down. Some quantum gravity theories, like loop quantum gravity, propose a possible solution. They suggest that as matter is compressed to near infinite density, quantum effects create a powerful outward pressure, like a cosmic spring that gets stiffer the more it's compressed. This would prevent the formation of a true singularity and could stop the collapse just before an event horizon forms. The result wouldn't be a black hole, but a quasi-stable, ultra-dense remnant, a quantum dark star. It would possess immense gravity, capable of severely bending light and trapping matter for eons, but it would lack the definitive one-way membrane of an event horizon. This fundamental difference in structure leads to a dramatic divergence in behavior, offering a potential way to finally tell these objects apart. A black hole, according to Stephen Hawking's work, should very slowly evaporate over trillions of years by emitting a faint stream of particles at its horizon, now known as Hawking radiation. However, for all practical purposes, a stellar mass black hole is a perfectly black and silent object. A quantum dark star with its surface of exotic quantum matter would tell a different story. Matter falling onto its surface wouldn't vanish silently. It could collide with a structure, potentially releasing bursts of energy or creating a complex atmosphere of trapped radiation and particles. Furthermore, its own version of quantum radiation could be significantly different from Hawking's prediction, potentially stronger or with a distinct energy signature that could, in theory, be detected. The true test and the holy grail for distinguishing these objects will come from next-generation observatories designed to study the immediate environment of these cosmic mysteries. The Event Horizon Telescope, which provided us with the first image of a black hole's shadow, could be key. A quantum dark star would cast a very similar shadow, but the intricate details in the ring of light around it, the photon ring, might exhibit subtle differences in its stability and structure compared to the clean shadow of a black hole's event horizon. Even more promising is the potential to detect the heat and light from matter just before it meets its fate. For a black hole, that material vanishes. For a quantum dark star, it would pile up, heat up, and could potentially create a faint X-ray glow that shouldn't be there according to the standard model. Perhaps the most revolutionary signature would be the direct detection of the object's radiation. While Hawking radiation from a black hole is too faint to ever be measured with current technology, the quantum radiation from a dark star's surface could be orders of magnitude stronger. Future space-based gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, could be sensitive enough to pick up the unique vibrational frequencies of these objects. A quantum dark star might ring like a bell when perturbed, sending out a specific harmonic signature in gravitational waves that a featureless black hole could never produce. Each of these potential signals represents a line in a cosmic fingerprint, a way to identify an object that has so far existed only in the equations of theoretical physicists, but whose discovery would forever change our understanding of the final fate of matter and the fundamental laws that govern our universe. Yet for all the violent grandeur of gamma-ray bursts and gravitational waves, some of the most compelling evidence for dark stars might be arriving not in a catastrophic flash, but in a silent, relentless rain of atomic fragments from deep space. We are constantly being bombarded by cosmic rays, high-energy particles, mostly protons, that race across the galaxy at nearly the speed of light. Most originate from well-understood sources like supernova remnants. But a tiny fraction possess energies so stupendously high that they defy all reasonable explanation, carrying the kinetic energy of a well-thrown baseball compressed into a single subatomic particle. The origin of these ultra-high-energy cosmic rays is one of the most enduring puzzles in physics, and their existence points to accelerators of almost impossible power hidden somewhere in the cosmos. What natural engine could possibly achieve this? The answer may lie not in the brilliant fury of a supernova, but in the immense silent gravity well of a dark star. To appreciate the sheer improbability of these particles, consider the famous "Oh my God" particle detected over Utah in 1991. This single proton was moving so fast that it possessed an energy of about 300 electron volts. In more relatable terms, it was traveling at 99.9999999999996% of the speed of light, carrying the energy of a major league fastball. The force required to accelerate a proton to that velocity is almost incomprehensible, far beyond the capabilities of any known celestial object. Even the most powerful supernova shockwaves fall short by orders of magnitude. These particles are the universe's way of telling us we are missing a key piece of its engine room, a natural particle accelerator of unimaginable ferocity. This is where the unique environment around a dark star becomes a prime suspect. Particle acceleration requires three key ingredients: a powerful source of energy, a magnetic field to steer the particles, and a vast region of space for them to gain speed. A dark star provides all three in extreme measures. Its immense gravitational field is the ultimate power source. Imagine a lone proton drifting through the interstellar medium, minding its own business until it enters the gravitational influence of a massive, isolated dark star. It begins to fall inward faster and faster, converting gravitational potential energy into sheer kinetic energy. But gravity alone isn't enough. The particle needs to be confined and focused to reach those extreme velocities. This is where the magnetic fields come in. The space around any massive object is not a perfect vacuum. It is threaded with magnetic fields and contains traces of ionized gas or plasma. Theorists propose that the chaotic, powerful environment just outside a dark star could support a naturally occurring version of a synchrotron, not unlike the massive rings we build here on Earth, but on a cosmic scale. As charged particles like protons are pulled in by gravity, they would spiral along these powerful magnetic field lines, being whipped around and around, gaining a little more energy with each pass. The sheer scale of the system is what allows for the incredible final energy. While a supernova shockwave might accelerate particles across a few light years, the magnetic funnel around a dark star could extend for hundreds or even thousands of light years, providing the endless runway needed for a proton to reach those oh my God energies before it is finally flung out, like a stone from a sling, back into the depths of the galaxy. The resulting cosmic ray signature would be a telling clue, because these ultra-high-energy particles are so rare and their paths are bent by magnetic fields during their journey. Tracing them back to a single point of origin is famously difficult. However, if a significant number of these anomalous events were traced back to seemingly empty regions of space, places devoid of supernova remnants or active galactic nuclei, it would be a powerful, albeit indirect, pointer to a hidden accelerator. A dark star, by its very nature, would leave no other electromagnetic trace of its particle accelerating activities. It would be a silent factory, its immense gravitational and magnetic machinery working in the dark. its only product a sporadic rain of atomic bullets fired randomly into the cosmos, each one a tiny, high-energy messenger from a place we cannot see. But perhaps the most extraordinary possibility lies not in the destruction of information, but in its creation or its origin from somewhere else entirely. This leads us to the most speculative and mind-expanding theory of all, that a dark star could be a remnant from a previous universe or a gateway to another one entirely within a multiverse. In the cyclical model of the cosmos, some theories suggest that our universe is just one in an endless sequence of big bangs and big crunches. In the final moments of a predecessor universe, as matter and energy were crushed into an unimaginable state, the conditions might have been right to form stable, ultra-dense objects that could somehow survive the rebirth of spacetime itself. A dark star, particularly a quantum one stabilized by exotic physics, could be such a relic, a cosmic fossil carrying the signature of an entirely different reality into our own. The scientific gateway into this wild idea is through the study of entropy and information. In our universe, the total amount of information and the arrow of time are intimately linked to the increase of entropy, a measure of disorder. A truly foreign object, one that originated from a universe with different fundamental constants or physical laws, might possess an entropy signature or information content that is fundamentally anomalous. It wouldn't quite obey the same thermodynamic rules as everything else around it. Detecting such an anomaly would be incredibly difficult, but theorists suggest that the way energy is distributed around a dark star or the specific spectrum of Hawking-like radiation it might emit could carry a subtle fingerprint of its exotic origin, a signature that simply doesn't compute within our single universe models. Exploring these concepts doesn't require abandoning science for pure science fiction. The scientific method can still be applied through a process of prediction and falsification. If a certain class of dark stars were hypothesized to be multiverse remnants, a specific, testable prediction about their properties would be made. For instance, they might be expected to have a very narrow range of masses, or to exhibit a specific spin distribution, or to be completely sterile, unable to accrete any matter from our universe because of a fundamental incompatibility. We could then search the sky for objects that match these very specific, very strange parameters. Finding even one that fits no other model would force us to consider possibilities that currently reside at the very farthest edges of cosmology. While the multiverse gateway theory remains a breathtaking long shot, it exemplifies the ultimate goal of the search for dark stars, to challenge our paradigms and remain open to the universe being far stranger and more wonderful than we have yet dared to imagine. And so we arrive at one of the greatest and most profound mysteries in all of modern cosmology, dark energy. This is the name we give to the mysterious force that is causing the expansion of our universe to not just continue, but to accelerate. It's a repulsive force, a kind of anti-gravity that makes up about 68% of everything in the cosmos, and to be perfectly honest, we have no idea what it actually is. The leading model treats it as a constant property of the vacuum of space itself, but this presents enormous theoretical problems. What if we've been looking at this puzzle from the wrong angle? What if dark energy isn't a smooth, uniform field, but is instead something that is being generated or released by specific processes happening within the universe? This is where our dark stars re-enter the narrative, not as passive objects, but as potential engines of cosmic change, whose very evolution might be intricately tied to the fate of the entire cosmos. To explore this radical idea, we need to consider the life cycle of a dark star, particularly a primordial one. Its existence is powered by the annihilation of dark matter particles at its core. But what happens when that fuel begins to run out? As the dark matter density within the star decreases, the outward pressure provided by the annihilation energy weakens. The star, which was once stabilized against its own immense gravity by this internal heat, can no longer hold itself up. It begins to collapse. This isn't a slow process, it's a catastrophic gravitational implosion. And according to some fascinating theoretical models, this collapse might not just form a black hole. It could trigger a phase transition in the very fabric of space-time, releasing a colossal amount of energy stored in the dark matter field, energy that could manifest as the repulsive force we call dark energy. Think of it like a cosmic battery. Throughout its long life, the dark star has been storing energy, not in a chemical form, but locked within the peculiar state of its core and the dark matter particles it contains. The collapse acts like a switch, discharging this energy directly into the universe. This wouldn't be an explosion of light and matter, but a sudden, localized inflation of space itself. If such events were happening continuously throughout the universe at different times and in different galaxies, they could collectively produce the observed effect of an accelerating expansion. Instead of a mysterious, smooth energy field everywhere, the acceleration would be the sum of countless individual events, like bubbles of repulsive force inflating within the cosmic web. This concept dovetails with another major puzzle known as the cosmic coincidence. Why are the energy densities of dark matter and dark energy roughly the same order of magnitude in our present epoch? It seems like a remarkable accident, but if dark energy is actually a product of dark matter decay or transformation, a process that would naturally link their abundances, then this coincidence isn't so strange after all. The dark stars, acting as the crucibles where this transformation occurs, would provide the missing link, explaining why the effects of dark energy became dominant around 5 billion years ago, as enough of these objects had reached the end of their life cycles and released their stored energy. The implications of this are staggering. It suggests that the accelerating expansion of the universe isn't a fundamental, preordained law of physics, but an emergent phenomenon, a side effect of the cosmos aging and its constituent dark matter evolving. In this model, the fate of the universe is not a cold, lonely heat death driven by a constant force, but a more dynamic and complex future. The rate of expansion could fluctuate over time, depending on the population and life cycles of dark stars. It opens up the possibility that this acceleration might not continue forever. It could slow down, stop, or even reverse if the process that fuels it eventually exhausts the available dark matter. Of course, this is a highly speculative theory, and the challenge of testing it is immense. Cosmologists are tackling it by looking for subtle signatures in the largest structures we can observe. If dark energy were being injected into the universe in discrete events linked to dark star collapses, it might not be perfectly uniform. There could be tiny variations in the expansion rate in different directions or correlations between the observed distribution of dark matter and the strength of the dark energy effect. The next generation of sky surveys, like the Legacy Survey of Space and Time at the Vera C. Rubin Observatory, will map the cosmos in unprecedented detail, searching for these very anomalies. They won't be looking for the dark stars themselves, but for the fingerprints they may have left on the entire universe, a permanent record of their transformative power written in the expanding space between the galaxies. Now, let's expand our view from single galaxies to the largest gravitationally bound structures in the universe, galaxy clusters. These are immense metropolises of thousands of galaxies, all swarming around a common center of gravity, embedded in a superheated gas that glows in X-rays. When we measure the total mass of one of these clusters by adding up all the stars and gas we can see, we find it accounts for only a small fraction of the gravity needed to hold the entire structure together. The rest is dark matter, but what if the dark matter isn't just a smooth, invisible fog? What if a significant portion of it is concentrated in the form of dark stars, acting as massive anchors that help shape the cluster's very architecture? The dynamics within a galaxy cluster are a complex ballet of visible and invisible forces. Galaxies zip around at thousands of kilometers per second, and that superheated intracluster gas at millions of degrees is shaped by the cluster's overall gravitational potential. Our models work well on the largest scales, but when we look closer, there are subtle anomalies. The motion of certain galaxies or the distribution of the hot gas can exhibit clumpiness or flows that suggest the gravitational pull isn't perfectly smooth. It's as if there are invisible mass concentrations, gravitational knots, within the cluster that are tugging on everything around them. While some of this can be explained by the dark matter halos of individual galaxies, the scale of these anomalies sometimes points to something more: free-floating, massive dark objects that are not associated with any single galaxy. These could be the dark stars we've been searching for, ejected from their home galaxies long ago and now drifting like invisible buoys in the cluster's vast sea. No object illustrates this concept more powerfully than the bullet cluster. This is not a single cluster, but the spectacular aftermath of a collision between two galaxy clusters. This cosmic crash provides a near-perfect natural experiment. During the collision, the different components of the clusters behaved in starkly different ways. The vast clouds of hot gas, which make up most of the normal matter, slammed into each other, creating a shock wave that we can see in brilliant X-ray images. But the gravitational mass of the clusters, mapped through the effect of gravitational lensing, did not slow down. It sailed right through the collision point, completely separate from the gas. This is considered the most direct evidence for the existence of dark matter. It clearly shows that most of the mass is something that does not interact with itself or with normal gas except through gravity. But the lensing map reveals another layer of intrigue. The centers of the two dark matter clouds are not perfectly smooth. They show substructure, smaller pockets of intense gravity. The standard interpretation is that these are the dark matter halos of the individual galaxies within each cluster. However, some of these gravitational hotspots appear offset or exist in regions with a very sparse population of galaxies. This opens the door to an alternative or additional explanation that some of these concentrated masses are in fact dark stars. These massive, isolated objects would have traveled along with the dark matter during the collision, their immense gravity contributing to these observed knots. They would be the ultimate dark matter tracers, highlighting its distribution with pinpoint accuracy. The presence of such objects could help solve lingering questions about cluster evolution. For instance, how do the densest cores of clusters form and maintain their stability? A population of massive dark stars sinking to the center of the cluster's gravitational well could provide a stable, unseen framework. Their combined gravity would act as a skeleton around which the visible galaxies and gas organize themselves. Furthermore, if these dark stars are the remnants of the first stars from the early universe, finding them in clusters would be a logical outcome. They would have naturally migrated to the deepest gravitational potentials over billions of years, making galaxy clusters the ultimate cosmic museums for these ancient relics. The search for these cluster-based dark stars relies on pushing gravitational lensing to its limits. Astronomers use the distorted images of thousands of background galaxies to create ever more detailed mass maps of clusters like the bullet cluster. They are looking for anomalies, tiny, pixel-scale distortions that could indicate a very compact, very massive object within the larger dark matter cloud. It's a painstaking process, like trying to find a single, specific fish by only seeing the subtle way it distorts the water currents around it in a vast, fast-moving school. Future telescopes, like the Nancy Grace Roman Space Telescope with its enormous field of view, will be able to perform this kind of ultra-precise lensing analysis on hundreds of clusters simultaneously, potentially revealing a hidden population of dark stars that have been shaping the largest structures in our universe from the shadows all along. Now, as we explore these candidates, we inevitably run into a fascinating case of cosmic mistaken identity. The theoretical profile of a primordial dark star, a massive, ancient, and potentially invisible object, sounds remarkably similar to another long-sought inhabitant of the cosmic dark, the primordial black hole. Both are theorized to have formed in the universe's first second. Both could account for a portion of dark matter, and both would appear to our telescopes as massive, unseen gravitational anchors. Untangling which is which, should we ever detect one, becomes a critical challenge, forcing astronomers to become cosmic detectives looking for the tiniest flaws in an otherwise perfect disguise. The confusion starts at their proposed birth. Primordial black holes are thought to be born directly from the incredible density fluctuations in the first moments after the Big Bang. Imagine the newborn universe as a seething, ultra-dense soup. In some regions, the density might have been so extreme that the gravity of that patch caused it to collapse directly into a black hole, bypassing the need for a star entirely. A dark star, by contrast, would have formed slightly later, not from a direct collapse of a density fluctuation, but through the more gradual accumulation of dark matter and gas, creating a structured object with a physical core. One is a singularity born from a snap decision of the cosmos. The other is a star that lived a strange, alternative life. This fundamental difference in origin leads to a key divergence in their very nature and, crucially, their potential numbers. Primordial black holes could theoretically exist across a vast spectrum of masses, from tiny, asteroid-sized objects to colossal ones thousands of times the mass of our Sun. They could be almost anywhere. Primordial dark stars, however, are predicted to form within a much more specific mass range. They need to be massive enough to gravitationally trap a sufficient amount of dark matter to power themselves, likely starting at many times the mass of our Sun. Their distribution would also be tied to the regions of the early universe that were rich in both dark matter and gas, potentially making them more clustered than their primordial black hole rivals. So if both appear as massive, dark objects, how do we tell them apart? The most promising method lies in a subtle but crucial distinction: the presence or absence of an event horizon. A black hole, by its definition, has one. A dark star, even an incredibly dense one, does not. This single difference opens up several avenues for detection. The first is through the search for a specific, faint electromagnetic signature. Matter falling onto a hard surface like that of a dark star would behave very differently than matter crossing an event horizon. It would likely pile up, heat up tremendously, and produce a last, desperate flash of light across various wavelengths before being absorbed. A black hole offers no such final farewell. Material simply vanishes with its energy emitted from a hot accretion disk outside the event horizon. A dark star might therefore have a faint, persistent glow or occasional flickers of radiation that a true black hole would lack, especially if it's drifting through a gas cloud. The second major differentiator is their gravitational footprint, specifically in microlensing surveys. When a massive object lenses a background star, the shape and duration of the brightening curve hold valuable clues. The signature of a point-like object with a clear event horizon, a black hole, is theoretically very clean. However, an extended object, even one as dense as a dark star, could potentially produce a slightly distorted or softer lensing signature. The light curve might exhibit subtle anomalies that wouldn't fit the perfect point mass model of a black hole. Future, ultra-precise microlensing experiments, perhaps with the Nancy Grace Roman Space Telescope, might be sensitive enough to detect this minute difference, effectively allowing us to feel the surface of a dark object from thousands of light years away. Perhaps the most revolutionary tool for this discrimination will be gravitational wave astronomy. The merger of two black holes produces a very specific chirp and ring-down signal as they spiral together and coalesce. Now imagine if one of the objects wasn't a black hole but a dark star with a surface. In the final, violent moments before merger, their surfaces would interact, creating additional vibrations and resonances in the gravitational wave signal, a kind of friction or turbulence in space-time that would be entirely absent in a clean black hole merger. LIGO, Virgo, and future observatories are constantly refining their templates to look for these exotic signatures. A single event that doesn't match the standard black hole model could be the first direct evidence that we're not dealing with a singularity, but with something entirely new and structured, a dark star finally revealing its true nature through the ripples it makes in the fabric of reality. But our search for these cosmic ghosts doesn't end in the distant halos of other galaxies or the depths of intergalactic space. The signs of their presence might be written in the familiar motions of our own celestial neighborhood, hidden in the strange, looping paths of ice worlds far beyond Neptune. For years, astronomers tracking the most distant objects in our solar system have noticed something deeply puzzling. A growing collection of small, icy bodies in the Kuiper belt and beyond are following orbits that are clustered, tilted, and aligned in a way that defies easy explanation by the known planets alone. Their paths seem to be shepherded, tugged by the gravity of something massive and unseen, a potential dark star lurking in the frozen hinterlands of our own solar system. This mystery centers on a group of objects known as extreme trans-Neptunian objects, or ETNOs. These are frozen worlds like Sedna and 2312 VP113, whose orbits take them hundreds of astronomical units from the Sun, far beyond the reach of Neptune's direct influence. According to our standard model of the solar system, the gravitational pulls from the known giant planets should have randomized the orbits of these distant objects over billions of years. Their long axes, their points of closest approach to the Sun, and the angles of their orbital planes should all point in random directions, yet they don't. Instead, they show a peculiar statistical clustering, as if an unseen hand is gently guiding them, preventing their paths from becoming completely scrambled. The most prominent hypothesis to explain this clustering is the existence of a ninth planet, a super-Earth or mini-Neptune-sized world, several times more massive than Earth on a distant elliptical orbit. But what if this hypothetical planet 9 isn't a conventional planet at all? What if it is, in fact, a dark star, not a primordial giant but a smaller, colder variant? Perhaps a rogue planet that was captured by the Sun's gravity, one that never ignited into a star because it was simply too small. This object could be a brown dwarf, a failed star that lacks the mass to sustain hydrogen fusion, making it incredibly faint and difficult to detect. Or it could be something even more exotic, like an ancient cold stellar remnant or a degenerate object of exotic matter that has been drifting through the galaxy for eons before being snared by our Sun's gravitational well. The evidence for such an object is purely gravitational, written in the intricate dance of these distant ice dwarfs. Computer simulations have shown that an object with a mass between 5 and 10 times that of Earth, on a highly elongated orbit that takes it from a few hundred to over 1,000 astronomical units from the Sun, could perfectly explain the observed orbital clustering. Its immense gravity would act as a distant shepherd, sculpting the paths of the ETNOs over millions of years, creating the precise patterns we see today. The beauty of this model is its predictive power. It tells astronomers exactly where to look for more of these shepherded objects, and indeed, new discoveries continue to fit the pattern, strengthening the case for a distant perturber. The hunt for this solar system dark star is one of the most exciting treasure maps in modern astronomy. Teams are using the world's most powerful wide-field telescopes, like the Subaru telescope in Hawaii and the Victor M. Blanco telescope in Chile, to methodically scan the vast proposed orbital path of this object. They are looking for a single, incredibly faint point of light moving slowly against the background stars. The challenge is immense. At such distances, even an object several times Earth's size would reflect only a tiny amount of sunlight, making it billions of times fainter than what we can see with the naked eye. Furthermore, its motion would be agonizingly slow. It might take years of observations to confirm its movement across the sky. Discovering this dark star would be a revolution in our understanding of the solar system's architecture and history. Its composition, revealed by spectroscopy, would tell us if it is a captured rogue planet from another star system, a primordial object that formed with the Sun but was ejected to the outskirts, or something entirely unknown. Its gravitational influence would rewrite the history of the solar system's formation, explaining not only the orbits of the neutrinos but potentially other anomalies, like the unusual tilt of the Sun's axis. It would mean our solar system has been hiding a massive, dark companion all along, a silent partner in our journey around the galaxy, its subtle gravity shaping the frozen frontier in ways we are only just beginning to comprehend. Stepping entirely outside the bounds of conventional physics, we now approach the most speculative and philosophically challenging idea of all. What if the influence of dark stars extends beyond gravity and particle physics, touching on something far more abstract? This is the consciousness hypothesis, a fringe theory that proposes these cosmic enigmas might have some connection to the nature of mind and awareness itself. It's a concept that resides firmly at the intersection of metaphysics and theoretical cosmology, and while it lies far beyond the scope of testable science, it offers a fascinating thought experiment about the universe's deepest mysteries. The foundation of this idea often begins with a principle known as panpsychism, the view that consciousness is a fundamental and ubiquitous feature of the physical universe, not merely an emergent property of complex biological brains. In this framework, even elementary particles might possess some rudimentary form of proto-consciousness. If that's the case, then the question becomes, could certain cosmic structures, by virtue of their immense mass, unique composition, or exotic physics, amplify or concentrate this fundamental quality? A dark star, with its incomprehensible density and its potential connection to dark matter, the universe's most dominant unseen substance, becomes a natural candidate for such a role. Proponents might suggest that these objects aren't just gravitational anchors, but focal points for a cosmic network of awareness, nodes in a vast, conscious cosmos. This line of thinking is often intertwined with interpretations of quantum mechanics that assign a role to the observer in collapsing quantum states. Some interpretations, though highly controversial, posit that consciousness itself is the mechanism that translates probability waves into definite reality. From this vantage point, a structure as massive and complex as a dark star could be imagined as a kind of permanent observer, its sheer presence constantly influencing the quantum fabric of spacetime around it in ways we cannot yet conceive. It's a notion that stretches the imagination to its breaking point, suggesting these objects might not just warp space, but the very nature of possibility and reality. It is absolutely vital to contrast this with the rigorous, evidence-based perspective of mainstream science. From a conventional astrophysical viewpoint, this hypothesis is untestable and therefore lies outside the realm of scientific inquiry. There is no instrument we can build, no observation we can make that could confirm or deny a link between gravitational anomalies and consciousness. The scientific method relies on falsifiability, the ability to prove an idea wrong, and this concept in its current form does not meet that criterion. Mainstream cosmologists would rightly argue that attributing consciousness to inanimate celestial objects is a category error, conflating the physical with the phenomenal in a way that doesn't yield predictive power or explanatory value. Yet the persistence of such ideas speaks to a deeper human desire. Dark stars represent the ultimate unknown, and consciousness remains the greatest unsolved puzzle within ourselves. It is perhaps inevitable that we would project our most profound mysteries onto the cosmos's grandest stages. These speculative theories, while not scientific, serve a different purpose. They are narrative tools that help us grapple with the sheer scale and strangeness of the universe. They remind us that our exploration of the cosmos is not just a cataloging of objects, but a journey to understand our place within it, blending hard data with the awe and wonder that first made us look up at the stars. For decades, the hunt for dark stars has been a story of inference and theory, of reading the subtle whispers of gravity in the motions of stars and the distortions of light. But we are now on the cusp of a new era, an age of astronomy where the tools to find these cosmic ghosts are either newly operational or on the drawing board, promising to turn speculation into discovery. The future of detection is a multi-pronged assault on the unknown, leveraging everything from the most sensitive infrared eyes ever built to instruments that listen to the very vibrations of spacetime. Leading this charge is the James Webb Space Telescope, an instrument that feels almost purpose-built to hunt for the universe's first monsters. Its unparalleled infrared sensitivity is the key. Remember, the light from the earliest primordial dark stars has been stretched by the expanding universe over billions of years, shifting it from visible light into the infrared part of the spectrum. Webb is uniquely equipped to see this ancient glow. Astronomers are not just staring into the void, they are using Webb spectrographs to analyze the chemical fingerprints of the very first galaxies. If they find a galaxy that seems too bright, too large, and too evolved for its incredibly young age, it could be a smoking gun. The brilliant, pervasive light from a single primordial dark star within that galaxy could be responsible for such an anomaly, its exotic energy source allowing structure to form faster and earlier than our standard models allow. Webb is essentially our time machine, peering back to the epoch of first light to see if the initial sources were familiar fusion stars or something far more strange and wonderful. While Webb looks for the ancient light of dark stars, a new generation of gravitational wave observatories is preparing to listen for their collisions. Ground-based detectors like LIGO and Virgo have opened our ears to the universe, but their sensitivity is tuned to the high-frequency waves from stellar mass black holes and neutron stars. To hear the deeper, lower-frequency rumbles of the true giants, we must go to space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, forming a gravitational wave observatory of breathtaking scale. LISA will be able to detect the mergers of supermassive objects, the very kind of dark stars that could be hiding at the centers of galaxies. The signal from such an event would be unmistakable. If 2 objects with millions of solar masses spiral together and their gravitational wave song shows the messy, resonant signature of objects with structure and surface, rather than the clean ringdown of pure black holes, it would be revolutionary proof that we have found something entirely new. On Earth, the search continues not by looking up, but by looking down, deep underground where the cacophony of the surface is silenced. In abandoned mines and beneath mountains, ultra-sensitive particle physics experiments are waiting for a different kind of signal. If dark stars are indeed powered by the annihilation of weakly interacting massive particles, or WIMP, then that process should be producing a continuous stream of neutrinos. Detectors like the IceCube Neutrino Observatory at the South Pole and the upcoming KM3 NET in the Mediterranean Sea are constantly monitoring for these ghostly particles. By tracing the path of a high-energy neutrino back to its source, they can point astronomers to a specific patch of empty sky. If multiple neutrinos are traced back to the same precise, dark point in space, a location with no visible object, no radio emissions, and no X-ray source, it could be the calling card of a stable dark star, steadily broadcasting its existence through this neutral messenger. It would be a direct detection of the engine itself, not just its gravitational influence. Finally, the field of astrometry, the precise measurement of star positions, is undergoing a revolution that will leave no corner of our galaxy uncharted. The European Space Agency's Gaia mission is already creating an unimaginably precise three-dimensional map of over 1 billion stars, measuring their positions, motions, and velocities with micro-arcsecond accuracy. Within this immense ocean of data, astronomers are fishing for stars that wobble. The gravitational tug of an unseen companion, whether a planet, a black hole, or a dark star, causes a star to trace a tiny, complex loop in its path across the sky. Gaia's ongoing data releases are allowing scientists to identify these wobbles with ever-increasing precision, revealing thousands of hidden companions. Among them, they hope to find anomalies, stars being tugged by massive objects that simply cannot be accounted for by any conventional explanation. These will be the addresses for future investigations, the coordinates where we will point every telescope we have, searching for the faintest glimmer of light or the softest whisper of radiation that might finally reveal the dark companions we have sought for so long. The future is not about a single magical instrument, but a symphony of data from space, from the ice, and from the underground, all converging to illuminate the dark. We have journeyed together through 25 of the most compelling and undiscovered candidates in the cosmos, from the primordial giants that lit up the infant universe to the quantum anomalies that might be holding our solar system's distant ice worlds in their gravitational grip. We have ventured into the hearts of galaxies to find invisible partners dancing with black holes, drifted through the void to find lonely wanderers between galaxies, and peered into the depths of particle physics to imagine objects that might not just use dark matter but could actually be creating it. Each of these candidates, from the dark star at the galactic core to the rogue planet in our own backyard, represents a fundamental challenge to our understanding of physics, gravity, and the very nature of reality itself. The potential for any one of these dark stars to be confirmed is not merely about adding a new entry to a catalogue of celestial objects. It is about triggering a paradigm shift in astrophysics. Imagine if we discovered a primordial dark star, a living fossil from the universe's first light. It would instantly provide a direct window into the nature of dark matter particles, something physicists in underground labs have been chasing for decades. Confirming a supermassive dark star at the heart of a quasar would force us to rewrite every textbook on active galaxies and black holes. Finding even one of these objects would be like finding a new set of rules for the universe, rules that are far stranger and more wonderful than we have ever dared to imagine. This isn't just about discovery, it's about transformation. It's about taking the countless unanswered questions we have about dark matter, dark energy, and the formation of structure, and finally having a new, tangible phenomenon to study, one that could weave these disparate mysteries into a single, coherent tapestry. This journey doesn't end when this video does. It continues in the work of astronomers scanning the skies, in the data from new telescopes, and in the curiosity of everyone who looks up at the night sky and wonders what's hidden in the darkness. The universe is under no obligation to make sense to us, and that is precisely what makes its exploration the greatest adventure of all. We are living in a golden age of discovery, where each new tool we build brings us closer to unveiling secrets that have been kept for billions of years. Stay curious, stay amazed, and never stop asking what if. Now we turn the question over to you. Which of these dark star theories captures your imagination the most? Do you think our solar system's hidden perturber, Planet 9, is a cold brown dwarf waiting to be found? Or does the idea of a consciousness-linked cosmic structure, as speculative as it may be, spark a sense of wonder about the universe's deepest possibilities? Share your thoughts in the comments below. We have only just begun to scratch the surface of the dark, and the most exciting discoveries are always the ones we have not yet even dreamed of.